Hello everyone, and welcome to today's session. I'm excited to have you here for Lecture 8, where we'll be diving into advanced mobile traffic interception and specifically how to bypass SSL pinning. This is part of our ITCR 613 Mobile Systems Security course. Today, we'll explore some of the more advanced techniques used to analyze and manipulate mobile traffic securely. We'll cover methods to bypass SSL pinning, which is crucial for understanding mobile security challenges. So, let's get started and see what these techniques are all about. By the end of this lecture, you will be able to understand the fundamental role that TLS and SSL play in mobile app security. I'll explain why these protocols are essential for protecting data in transit and how they help establish trust between your app and servers. We'll also cover the limitations of relying solely on standard certificate authorities, or CAs, and why SSL pinning is necessary to enhance security further. Additionally, I'll guide you through setting up a dynamic analysis environment so you can intercept mobile app traffic effectively. We'll discuss the technical principles behind different SSL pinning implementations, helping you understand how they work under the hood. Furthermore, I'll show you how to methodically use advanced tools like FRIDA and objection to bypass SSL pinning when needed, which is crucial for testing and security assessments. Lastly, I'll help you develop and implement effective countermeasures as developers to strengthen your app's defenses against common attacks. All these points connect to our overall theme of understanding and improving mobile app security, equipping you with practical skills and insights to protect your applications. When we talk about the foundation of secure communications, we need to understand TLS, PKI, and the threat of man-in-the-middle attacks. These are the core components that keep data safe during transmission. TLS, or Transport Layer Security, is what encrypts the connection, while PKI, or Public Key Infrastructure, manages the digital certificates that verify identities. But despite these defenses, attackers can still attempt MIT-M attacks to intercept or manipulate data. This is where the defense mechanisms come into play, particularly SSL pinning. SSL pinning enhances security by ensuring that the app only trusts specific certificates, preventing attackers from using fake certificates to intercept traffic. Knowing why and how to implement SSL pinning is crucial for strengthening your app's security posture. Moving on to our arsenal of tools and setup, we use emulators, proxies, and tools like FRIDA for runtime instrumentation. These tools help us analyze and test the security of mobile apps effectively. Setting up a lab environment with these tools allows us to simulate attacks and understand potential vulnerabilities better. In the reconnaissance phase, we attempt a standard MIT-M attack to see if the app is vulnerable. This step is fundamental before trying more advanced techniques, as it helps identify weak points in the communication security. The kill chain approach is a systematic method for bypassing pinning. It involves understanding each step an attacker might take and developing strategies to counteract or bypass these measures. We explore several techniques to bypass pinning. First, bypassing Android's network security config, which can sometimes disable pinning protections. Second, patching and repackaging the APK to remove pinning checks. Third, using runtime instrumentation with FRIDA to manipulate code on the fly. Fourth, leveraging automated tools like objection for quick bypasses. We'll also look at a case study involving a heavily secured banking app. This will illustrate the practical application of these techniques and the challenges faced in real-world scenarios. Finally, we emphasize implementing robust pinning strategies. It's not just about bypassing, but also about understanding how to reinforce your app's defenses effectively. Throughout this presentation, our goal is to give you a comprehensive understanding of how these security measures work, how they can be tested, and how to improve them against sophisticated attacks. Let's talk about the purpose of TLS and SSL. Essentially, they are designed to ensure three key things: confidentiality, integrity, and authentication between the client and the server. This means that the data we exchange is kept private, hasn't been tampered with, and both parties can verify each other's identities. Now moving on to the standard PKI trust model. In this setup, our app trusts a list of pre-installed certificate authorities, or CAs. When we connect to a server, that server presents a certificate. If this certificate is signed by one of those trusted CAs, the connection is considered secure and is allowed to proceed. However, there's a vulnerability here. This model can be quite brittle. If an attacker manages to add a malicious or custom CA certificate to your device's trust store, say by installing a tool like Burp Suite or Charles Proxy, they can essentially impersonate any server. What does that mean in practice? Well, your device and app will trust the proxy's certificate for sites like API, bank, com, allowing the attacker to inspect or even modify all the traffic passing through. This is a significant security risk because it undermines the trust model at its core. To connect this to the bigger picture, understanding these foundational concepts, TLS, PKI, and the man-in-the-middle attack is crucial. They highlight how our security can be compromised if trust isn't carefully managed and why robust measures are essential to protect sensitive data. Let's take a closer look at the core concept here. The mobile app pins to a specific expected server identity, which means it ignores the device's global certificate authority trust store. This is a key part of SSL pinning because it ensures that the app only trusts a particular server, reducing the risk of man-in-the-middle attacks. So what exactly is pinning? There are two main types. First, certificate pinning, where the app holds a copy of the server's exact certificate. This way, it can verify that the server's certificate matches what it expects. Second, public key pinning, where the app holds the server's public key instead. This approach is a bit more flexible because it can survive certificate renewals as long as the key remains the same, which is a big advantage in many scenarios. Now, how do we implement this? There are platform-specific methods, like Network Security Config on Android and NS App Transport Security on iOS, that help with pinning. Then, there are library-specific options, such as OK HTTP's Certificate Pinner or AF Networking's SSL Pinning Mode. Developers can also create custom trust managers or delegates if they need more control over the process. To sum up, SSL pinning is a powerful defense mechanism. It locks the app to a specific server identity, making it much harder for attackers to intercept or impersonate the server. This is a critical part of securing mobile communications and maintaining trust in the app's data exchanges. All right, let's discuss the prerequisites for this lab setup. First, you'll need either a rooted Android emulator or a physical device, or alternatively, a jailbroken iOS device. This is essential because we need deep system access to effectively intercept and modify app behavior. Without this level of access, our ability to perform thorough analysis is limited. Next, we'll be using some core tools. One of these is a MIT-M proxy, like Burp Suite Professional or OWASP Zap, which allows us to intercept and analyze network traffic between the app and its servers. For disassembling Android APKs, JADX GUI is our go-to tool. It helps us understand the app's inner workings. On the runtime side, Frida is fundamental. It's our core engine for instrumentation, enabling us to hook into live processes and manipulate them on the fly. Complementing that, Objection acts as a wrapper around Frida, making it easier for pen testers to automate and streamline our tasks. The main goal of this lab is to intercept all HTTPS traffic from the target application. To do that effectively, we need to set up our environment correctly, making sure all these tools work seamlessly together. This setup is crucial because it allows us to analyze encrypted data, understand how apps communicate, and identify potential security issues. So, by ensuring we have the right device and these core tools in place, we can perform comprehensive security testing and deepen our understanding of app behavior and security posture. Let's walk through the procedure step by step. First, you'll need to configure the proxy settings on your device or emulator. This step is crucial because it directs the traffic through the proxy, allowing us to observe and analyze the data. Next, you must install the proxy's CA certificate onto the device. This certificate essentially acts as a trusted authority, enabling the proxy to intercept HTTPS traffic without raising security alerts. Once that's set up, launch the target app and perform the actions you want to analyze. If there's no SSL pinning in place, you'll see all HTTP and HTTPS traffic clearly in the proxy. This means you can inspect requests and responses easily. However, if the app uses pinning, specifically certificate pinning, the results are different. You'll notice connection errors in the proxy logs. The app might fail to connect, crash, or show a network error message. Common log messages indicating this include certificate pinning failure or JAVAX, NET, SSL handshake exception. This step, reconnaissance, is essentially our first move in a man-in-the-middle attack attempt. It's about seeing how the app reacts when we try to intercept its traffic, which helps us understand the security measures it employs. All right, let's dive into how we escalate our techniques, starting from the simplest to more complex methods. First, we have the low-hanging fruit approach, which involves basic platform configurations, like working with the NSC settings. This is often the easiest entry point because it usually requires minimal effort, but can still be quite effective. Next, we move on to static binary modification. Here, we patch the binary and repackage it, allowing us to alter the application's behavior without needing to run it in real time. This method is a bit more involved, but offers a lot of control. Then, we step into advanced runtime manipulation, where tools like Frida come into play. Hooking with Frida enables us to dynamically intercept and modify app functions as they run, giving us a powerful way to bypass protections at runtime. Finally, we have automation, specifically using objection for rapid testing. This allows us to streamline our process, quickly applying our techniques repeatedly and efficiently. All of these methods fit into the broader theme of the presentation, which is about understanding and bypassing security measures through a structured, step-by-step approach. This is what we call the kill chain, a systematic way to methodically approach and bypass security controls, moving from simple to more sophisticated techniques. Let's take a closer look at what NSC is. Basically, it's an XML file that allows developers to customize network security settings without having to write any code. Think of it as a configuration file that controls how your app handles security policies. Now, the pin refers to a pin set element within the network's security config, XML file. This is where the security pins are defined, essentially specifying trusted certificates or endpoints. Moving on to the bypass technique, first, you need to use a tool to decode the APK. This tool helps you unpack the application so you can access its internal files. Next, once decoded, locate and examine the network security config, XML file. This is where the security settings are defined. Then find the pin set element and look for the critical attribute, Android, enforcement equals, enforced. This attribute enforces the security pin, meaning the app strictly adheres to the specified security policies. To bypass this enforcement, you can change enforced to disabled, or simply remove the entire pin set element altogether. After making these changes, repackage and resign the APK. Finally, install the modified APK on your device. It's important to note that this technique has limitations. Since re-signing the APK breaks signature verification, apps that rely on signature checks may no longer work correctly after modification. Now, let's move on to Technique 2, which is patch and repackage at the code level. This approach involves directly modifying the application's code to address vulnerabilities or add new features. It's a more hands-on method that requires a good understanding of the application's structure and logic. The key idea here is to identify the specific parts of the code that need fixing and then patch them accordingly. Sometimes, this means injecting new code or reworking existing code to improve security or functionality. Repackaging, on the other hand, involves taking the patched code, reassembling the application, and deploying it again. This technique is powerful because it allows for precise modifications, but it also demands careful testing to ensure nothing breaks. Overall, Patch and repackage is a vital strategy in the toolkit for maintaining secure and reliable software. It ties back to our overall theme of proactive security measures through detailed, code-level interventions. So, what is Frida? Well, it's a powerful and flexible dynamic instrumentation toolkit. It allows us to inject our own scripts directly into black box processes, meaning processes we don't have the source code for. Instead of modifying the actual app file, Frida lets us change its behavior on the fly, in memory, as it runs. This makes our modifications much more adaptable and less detectable. The core idea here is that we write a JavaScript script that Frida injects into the app process. Think of this script as a way to hook into specific functions that are responsible for security checks, like pinning validation. Once injected, it intercepts calls to those functions and can alter their behavior, most commonly by forcing them to return a success value. This effectively neutralizes the check without needing to modify the APK itself. Why is this approach so powerful? For one, it bypasses signature checks because the original APK remains unchanged. That means we can test or reverse engineer apps without triggering built-in protections. Plus, it works even if the code is obfuscated, as long as we can identify the correct functions to hook. And importantly, there's no need to repackage the app, keeping the process clean and straightforward. So, to summarize, runtime instrumentation with Frida offers a flexible, in-memory way to manipulate app behavior, making it an essential tool in our toolkit for dynamic analysis and security testing. All right, let's take a closer look at this Frida JavaScript script in action, specifically how we're hooking into OK HTTP. What we're seeing here is a practical example of how Frida can be used to intercept and manipulate network requests made by an Android app. By injecting this script, we can monitor the details of HTTP calls, modify responses, or even block certain requests altogether. This approach is incredibly powerful for security testing and reverse engineering. The key concept here is hooking into the OK HTTP library, which is widely used for network communication. This allows us to gain deep visibility into app behavior without altering the original code. Connecting this back to our overall theme, it demonstrates how dynamic instrumentation tools like Frida enable us to understand and analyze app functionalities in real time, providing insights that static analysis alone might miss. So, what does objection actually do? Well, it comes with pre-built scripts that help you quickly hook into common pinning methods used in OK HTTP, Trust Manager, and other core classes. Essentially, it automates the application of the Frida technique, making the process much smoother. Now, for those who might not be familiar, Objection is a runtime mobile exploration toolkit powered by Frida. It automates many of the routine tasks we often face during testing or reverse engineering, saving us a lot of time and effort. The real power here is automation. With Objection, you don't need to write complex scripts for common pinning libraries. A single command can often bypass pinning across multiple layers of the app, which is a huge time saver. Specifically, under Technique 4, we're talking about automated bypass with Objection. This approach is designed to streamline the process and allow us to quickly and effectively bypass pinning protections without extensive manual scripting. It's all about making our work more efficient and less error-prone. Let's take a closer look at this case study involving a hardened banking app. What we're really focusing on here is how security measures are implemented in real-world financial applications to protect sensitive data. As we analyze this, you'll notice that the key points revolve around assessing the app's defenses against common attack vectors, identifying vulnerabilities, and understanding how these defenses align with industry best practices. This case study exemplifies the importance of a layered security approach, which is a recurring theme throughout our presentation. It shows us that no single security measure is enough. Rather, a combination of strategies is necessary to create a truly resilient application. By examining this example, we can better appreciate how rigorous security testing and continuous improvement are essential in safeguarding banking apps against evolving threats. Let's walk through the lab together, putting everything we've discussed into practice. This slide is all about tying it all together, applying the concepts we've learned in a real-world context. As we go through each step, focus on how these components connect and support the overall process. Remember, the goal is to see how each part fits into the bigger picture, ensuring that we understand not just the how, but the why behind each action. This hands-on approach helps solidify your understanding and prepares you to apply these skills independently. So, keep in mind the key principles we've covered, and let's see how they work in a practical setting. Let's talk about the importance of defense in depth, which is really the key to robust security. First, pinning to the public key is more resilient than certificate pinning because it allows you to verify the actual key rather than just the certificate, making it harder for attackers to bypass. Next, using multiple pins, or what we call backup pins, helps you rotate keys without breaking the app. This keeps your security flexible and adaptable. It's also crucial to implement pinning at multiple layers. For example, in a high-level library like OK HTTP, and also within a custom trust manager. This layered approach makes it significantly harder for an attacker to bypass all defenses. Another important point is obfuscating your pinning logic. If you make it difficult for someone to analyze or patch your code easily, you add another layer of protection. Finally, perform runtime integrity checks. Verify the APK signature at runtime to ensure it hasn't been tampered with. Detect if the device is rooted or jailbroken to prevent running on compromised devices, and check for the presence of debugging tools like Frida or other instrumentation frameworks. These checks act as active defenses, catching malicious activity in real time. All these strategies together form a comprehensive defense, making your app much more resilient against various attacks. It's about layering your defenses so that even if one layer is compromised, others are still in place to protect your app and your users. Let's talk about runtime application self-protection, or RASP for short. Essentially, these are security controls that are embedded directly within the application itself. This means the app can actively monitor and protect itself from threats during runtime, in real time. For example, RASP can detect if tools like Frida's server are running on the device, which are often used for reverse engineering or tampering. It can also identify if common pinning bypass techniques are being employed to defeat SSL/TLS protections. When such threats are detected, RASP can respond immediately by wiping sensitive data from memory, shutting down the application, or even entering a dummy mode to confuse attackers. This advanced form of defense is crucial because it allows the app to adapt and respond dynamically, adding a strong layer of security against runtime attacks. It really exemplifies how security can be integrated directly into the application's core, aligning with our overall goal of making applications more resilient against evolving threats. Let's talk about some limitations of bypass techniques. While they can be useful, it's important to recognize that strong RASP and integrity checks can make bypassing quite difficult. These security measures are designed specifically to prevent tampering and ensure the software hasn't been altered. Additionally, certain server-side security mechanisms, like client certificate authentication, are inherently harder or even impossible to bypass using these techniques. They are meant to protect critical parts of the system that can't be bypassed easily. Now, moving on to ethical and legal considerations. These techniques should only be used in the context of authorized security testing. That's a key point. Using bypass techniques on software you don't own or without permission is illegal and can have serious consequences. Always make sure you're operating within a well-defined scope and have explicit permission before attempting any of these methods. It's essential to stay within legal boundaries and adhere to ethical standards to avoid any potential issues. Let's talk about SSL pinning. It's a crucial defense in-depth mechanism, but it's important to remember that it's not a silver bullet. While SSL pinning can significantly increase security, no single measure is foolproof on its own. Now, when it comes to devices that are rooted or jailbroken, the attacker's advantage becomes quite substantial. These devices give attackers more control and make bypassing security measures, like SSL pinning, much easier. One of the most powerful tools available for runtime manipulation and bypassing pinning is Frida. It's incredibly versatile and allows attackers to inject scripts into running processes, making it a real challenge to defend against. That's why a layered approach is essential. We need to combine multiple defenses: SSL pinning, obfuscation, integrity checks, and runtime application self-protection or RASP. Relying on just one layer leaves us vulnerable. It's also worth noting that the game between attackers and defenders is ongoing, like a constant cat-and-mouse chase, especially in the mobile space. Attackers keep evolving their techniques, so our defenses must be just as dynamic. To wrap up, the key takeaways are that no single security measure is enough on its own. We need layered, adaptive strategies to effectively protect our mobile applications. All right, for your required reading and labs, I recommend starting with the OWASP MSDG, specifically the chapter on testing network communication. This will give you a solid foundation on how to analyze and secure network interactions. Next, check out the Frida documentation at Frida, re/docs, which is an incredibly powerful tool for dynamic instrumentation and testing mobile apps. It's essential for understanding how to manipulate app behavior during security assessments. Also, don't forget the objection wiki at GitHub, com/sensapost/objection/wiki, which builds on Frida and offers practical commands for mobile security testing. These resources are key because they tie into the overall theme of understanding and testing application security by exploring how data flows and interacts within the system. Mastering these tools and concepts helps us identify vulnerabilities and strengthen defenses. So, diving into these readings and labs will equip you with the practical skills needed for real-world security assessments.